In this lecture, we're going to look at another iterative method for approximating the solutions to equations called Newton's method. And as we'll see in a later lecture, this method kind of fits into the loophole we saw earlier that limited most iterative methods to strictly linear convergence. All right, so first let's get the formalities out of the way. We're going to start with a C1 function, that is a function that has a continuous first derivative on a closed interval, and that has a root p on that interval. And we'll let P0 be our first approximation of that root. And I do have one extra little caveat here at the end. We're also going to require that the derivative of the function is not 0 at that approximation, right? And you'll see why that's important as we get a little further into this. All right, so next, let's look at the graph of the function, right? Let's just sketch out something like this for us to look at. The root P that we're looking for is here. And I'll put our first approximation, P0, over here. Now that value corresponds to a point on the graph, P0, comma, f of P sub 0. Now look at the tangent line to the graph at that point, specifically at its x-intercept. And notice how that intercept is a lot closer to P than our original approximation was. That's the central idea of Newton's method. We're going to start with an approximation, find the x-intercept of the tangent line at that point, and that's going to be our next approximation. All right, so all that's left is to look for a formula for that x-intercept. Now, we know that the line goes through the point P0, comma, f of P sub 0, and we know that its slope is f prime of P sub 0. So if we substitute those values into the point slope equation, we get this. Now, this was a calculus class. I solved this for y and get into the slope-intercept form. But our goal here is to find an equation for the x-intercept. All right, so if we call that P1, comma 0, I'll substitute those values back into this equation. And when I do that, it becomes this. All right, now, if we solve this equation for P1, we get this formula for the next approximation in our process. And I'm going to go one step further. I'm going to generalize this. Instead of having 1 and 0, I'm going to say Pn plus 1, the next approximation, is equal to P sub n minus f of P sub n over f prime of P sub n. And that's our formula. Right? That is the function, the expression that we're going to iterate to get numbers in a sequence that is going to ultimately converge to that actual root of the function. And looking at this, hopefully you can see now why it was important up here to require that the derivative of the approximation not equal 0. Right, we've got that down here in the denominator of the fraction. Right, if that was 0, you can't divide by 0 and the whole process would fall apart. So in the next lecture, we're going to look at another method for deriving this formula that's more calculus-based. Right? It uses the Taylor series of the function. Now, this has some advantages over the geometric or algebraic method that we use here, and it's going to point us in the direction of a bound on the method's error. So now in the next lecture, if you're looking to skip ahead, in the next lecture after that, if you're looking to skip ahead, we'll start looking at examples of how to use this method to find solutions to some specific equations.